In this grade 12 chemistry tutorial, I'm going to go over two problems that you might see in atomic theory. So in our first example, we have a violet line with a wavelength of 410 nanometers. We need to find the energy of the photons, which are the quanta of light, which give rise to this line. So to do that, we can use this equation where the energy is equal to Planck's constant times the frequency. But we weren't given the frequency, we were given the wavelength, which is lambda. Now from our wave equation, we know the speed of this wave, which in this case is light, so it's equal to c. It's equal to the frequency times the wavelength. So if we just rearrange this, we have that divide both sides by wavelength, and we have that the speed of light over wavelength is equal to frequency. So knowing that, I can rewrite this here as E equals Planck's constant, and instead of frequency, I'm going to write c over lambda. So hc over lambda. So now I can calculate this. So let me just calculate it over here where I have some more space. So the energy of this photon is equal to Planck's constant, which we have as 6.6 times 10 to the minus 34 joule seconds, times the speed of light, which is 3.0 times 10 to the 8 meters per second. And that's all divided by that wavelength. That wavelength is in nanometers. So we want this in SI units, or our base units, which is meters. So what we have to do is take that 410 and multiply it by 10 to the negative 9 to get our nanometers converted to meters. So now that we've done that, we get an energy of 4.8 times 10 to the minus 19 joules. Now as an extension, if the question wanted to ask what is it in kilojoules per mole, which is a common question, we can first convert this to kilojoules by multiplying by 1 kilojoule for every 1,000 joules. And that'll give us kilojoules, which is 4.8 times 10 to the minus 22 kilojoules. And that is for every atom. So then to get it in moles, instead, what we're going to do is multiply by Avogadro's number. So we have 6.023 times 10 to the 23 atoms per mole. So that's going to get us in kilojoules per mole, which is a value of 2.9 times 10 to the 2, or 290 kilojoules per mole. Alright, in our second example, we have to show that the transition of electron from energy levels n equals 4 to n equals 2 in a hydrogen atom give rise to the blue-green spectral line of wavelength 486 nanometers. So what we have is our electron. Here's n equals 1, 2, 3, 4. So sorry, I'm not the best artist here. So it's going from 4 down to 2. And so it's going to lose some energy, and that energy is going to be emitted as a photon of what we're trying to see is whether or not that photon has a wavelength of 486 nanometers. So to do that, let's find out how much energy this electron loses. So we have this equation here in our chemistry class. The energy level in hydrogen at the nth level is equal to negative 2.18 times 10 to the minus 18 joules, all divided by n squared. So what we're going to do is we're going to figure out how much energy did it have at the fourth energy level, how much energy does it have at the second energy level, and then we'll find the difference to see how much it lost when it dropped from 4 to 2. So let's try 4. So we have minus 2.18 times 10 to the minus 18 joules. And for our fourth, that's 4 squared. And that gives us negative 1.36 times 10 to the minus 19 joules. So let's do the same for the second energy level. And this time we divide by 2 squared. And that gives us minus 5.45 times 10 to the minus 19 joules. Alright, so let's find the difference. So when you find the difference, it's always final minus initial. So we're going to do E2 final. That's our final state because we dropped to 2. Minus our initial state, we were originally at 4. So we have minus 5.45 times 10 to the minus 19 joules minus, right, the difference. Difference means to subtract. And then we have this negative, so we have a double negative here, which will be a positive, times 10 to the minus 19 joules. And when we do that, we get negative 4.09 times 10 to the minus 19 joules for each atom. Now this is how much energy is lost. So therefore, this photon will gain that much energy. So this photon has an energy of that positive value, 4.09 times 10 to the minus 19 joules. All right, let's figure out what wavelength of light has this much energy. So we have this equation, right? The energy of a photon is Planck's constant times the frequency. But just as our previous example, we're going to change frequency because we're looking for wavelength. We're going to change it to the speed of light divided by that wavelength. Okay, then we can cross multiply. So we get wavelength is equal to Planck's constant times the speed of light divided by the energy. So let's try this. We have Planck's constant, 6.626 times 10 to the minus 34 joule second. I'm going to run out of space here. Speed of light is 3 times 10 to the 8 meters per second. All over our energy, which is 4.09 times 10 to the minus 19 joules. Okay, you can see our units work. Joules cancels, seconds cancels, and we're left with meters, and we get 4.86 times 10 to the minus 7 meters, which is equal to 486 nanometers. I'll take that. I hope that helped everyone.